Across the face of the sun, something enormous has been unfolding. Dark regions have appeared where the magnetic architecture of our star has opened towards space, allowing streams of charged particles to escape outward at extraordinary speeds. At the same time, Earth's volcanic landscape has been anything but quiet. Mount Etna has produced explosive and effusive activity. Fuego has intensified. Taal has registered a sharp burst of volcanic earthquakes. Puracé has entered heightened unrest. Kīlauea continues erupting. Indonesia remains crowded with restless volcanoes. And now, the sun has delivered another powerful signal. The timing is difficult to ignore. On August 20th, 2026, solar active region AR4513 produced an M8.1 flare, the strongest flare of that period. NOAA classified the event as an R2 moderate radio blackout, while observations detected a Type 2 radio sweep and a coronal mass ejection signature. The estimated shock speed associated with the Type 2 event reached roughly 1,200 kilometers per second, or about 746 miles per second. Yet the most important question is not simply what the sun did, it is what Earth may do next. A coronal hole is not literally an empty cavity punched through the sun, and its apparent dimensions depend upon how the structure is measured and projected across the solar disk. The sun itself is roughly 109 times wider than Earth, meaning that a feature spanning a major fraction of the solar disk can look astonishingly large when viewed in extreme ultraviolet imagery. NASA explains that coronal holes are regions of lower density plasma associated with magnetic field lines opening outward into interplanetary space. That distinction does not make the phenomenon less dramatic. In fact, it makes it more important. A coronal hole is effectively an opening in the sun's magnetic architecture through which the solar wind can escape more freely. Instead of behaving like a sealed atmosphere, the corona contains regions where magnetic field lines stretch outward and connect with interplanetary space. Plasma follows those open pathways. The result can be a high-speed solar wind stream that travels hundreds of kilometers per second, eventually reaching Earth and interacting with the planet's magnetosphere. This is where the solar story becomes an Earth story. Earth Evolution's Energy Analytics page provides a striking window into this connection by placing solar imagery, geomagnetic information, radiation belt measurements, auroral predictions, seismic activity, and Schumann resonance data within the same monitoring environment. The page itself warns that Schumann resonance measurements are sensitive to local atmospheric electrification, wind-related vibration, and microphonic noise, so they cannot independently establish a global solar effect. But the broader principle is important. Earth is not an isolated geological machine. It exists inside a constantly changing electromagnetic environment whose strongest disturbances originate from the sun. That environment is becoming increasingly interesting as solar activity intensifies and changes on timescales ranging from minutes to years. Solar flares are explosive releases of electromagnetic energy. Coronal mass ejections propel enormous quantities of magnetized plasma into space. Coronal holes produce persistent, high-speed solar wind streams rather than single explosive blasts. These are different phenomena, but they can overlap in time, creating complicated conditions around Earth. The result may include radio blackouts, energetic particle enhancements, changes in the magnetosphere, auroras, ionospheric disturbances, and geomagnetic storms. Earth's atmosphere and magnetic field become part of the experiment. The August 20th flare is particularly significant because it came from AR4513, a region that had been developing magnetic complexity as it rotated toward an increasingly Earth-facing position. NOAA reported that the region produced the M8.1 event at 11:42 UTC, along with additional M-class activity. The associated coronal mass ejection signature was detected in coronagraph imagery, although the initial analysis indicated no Earth-directed component. That detail matters enormously. A solar flare can be powerful without producing a major geomagnetic storm at Earth, because geometry determines whether the resulting ejecta actually intersects our planet. Yet the sun does not need to launch a direct hit for its magnetic behavior to matter scientifically. Coronal hole high-speed streams can arrive from regions of open magnetic field and modify the solar wind environment over several days. The Belgian Solar Influences Data Analysis Center reported that a northern mid-latitude coronal hole had begun crossing the central solar meridian, with an associated high-speed stream potentially arriving at Earth from August 21st onward. Earlier in August, other coronal holes were already producing high-speed streams and geomagnetic disturbances, demonstrating that the Sun's open magnetic structures were active well before the latest major flare. This is where the apparent coincidence with volcanoes becomes compelling. The planet's volcanoes were already showing signs of unrest before the M8.1 flare. Mount Etna was producing explosive and effusive activity during the August 10th through 16th period. Fuego intensified earlier in the month. Taal experienced an abrupt increase in volcanic earthquakes around August 15th. Puracé entered a period of heightened concern. Kīlauea remained active. These observations mean the relationship cannot honestly be reduced to a simple chain in which one solar flare occurred and then volcanoes immediately erupted. The chronology is much more complicated, but complexity does not make the scientific question disappear. It makes it more interesting. If solar forcing has any measurable influence on volcanic systems, the effect would not necessarily resemble flipping a switch. A volcano does not sit dormant and wait for sunlight or solar wind to push a button. Magma systems are governed by pressure, temperature, volatile content, crustal permeability, tectonic stress, hydrothermal circulation, and the geometry of fractures. Solar forcing, if it contributes, would have to operate through an indirect physical pathway, potentially nudging a system already close to failure rather than creating volcanic pressure from nothing. That distinction is essential because it changes the question from whether the sun can create a volcano to whether solar disturbances can influence the timing or intensity of processes already occurring inside a stressed Earth system. A loaded fault does not need a gigantic external force to rupture if it is already close to its critical threshold. A pressurized volcanic conduit can behave similarly. Tiny perturbations may have little effect on a stable system while producing a measurable response in a system already poised near instability. This threshold concept is central to understanding why researchers continue examining possible solar and geophysical connections. One of the most fascinating areas of research involves statistical relationships between solar activity and volcanic behavior over long periods. A 2022 study by I. Vasilieva and V. Zharkova examined 270 years of terrestrial volcanic eruptions against solar activity and magnetic field variations. The researchers reported a strong correlation between volcanic eruption frequency and a solar magnetic field component across multiple solar cycles, with a prominent approximately 22-year periodicity. Correlation does not establish the mechanism, but findings like these keep the question alive because they suggest that long-term solar variability may deserve closer examination alongside conventional volcanic drivers. Other research takes a different approach, looking at energetic solar events and their ability to produce disturbances throughout the coupled Sun-Earth system. Solar flares can generate intense electromagnetic radiation almost immediately. Coronal mass ejections can send magnetized plasma across interplanetary space. High-speed solar wind streams can repeatedly interact with Earth's magnetic field as the Sun rotates. These processes alter the magnetosphere and ionosphere, creating electromagnetic and atmospheric responses that propagate through different layers of the Earth system. The unresolved question is whether any portion of that disturbance can penetrate deeply enough or couple efficiently enough to influence geological systems. That question becomes especially intriguing when researchers consider the electrical properties of the atmosphere and crust. Earth is not electrically inert. The ionosphere, magnetosphere, atmosphere, oceans, crust, and mantle participate in a complex electromagnetic environment. Geomagnetic storms generate electrical currents in the ground, while changing magnetic fields can induce electric fields over large areas. These effects are well established in space weather science. What remains much more controversial is whether such electromagnetic disturbances can significantly alter volcanic or seismic processes at depth. The mechanism would need to overcome enormous geological energy barriers while producing a measurable effect. Earth Evolution's monitoring page is useful precisely because it puts several different measurements into view. Its seismic section emphasizes that earthquake energy rises enormously with magnitude, while its radiation belt and auroral sections show how solar particles and magnetic disturbances interact with Earth's space environment. Its Schumann resonance display adds another layer, but the site explicitly cautions that the signal is affected by local atmospheric conditions and instrument noise. That caution is important. A spectacular graph may show that Earth's electromagnetic environment changed, but it does not automatically prove that a volcano responded to that change. The same caution applies to seismic energy charts. A day containing many earthquakes can appear dramatically different from a quiet day, but earthquakes naturally cluster because tectonic systems are heterogeneous and faults interact. Volcanoes add another layer of complexity because volcanic earthquakes can result from fluid movement, magma migration, fracture, pressure changes, or hydrothermal processes. Therefore, a spike in global seismic energy occurring after a solar storm would be interesting, but it would still require statistical comparison against long-term background behavior. Without that baseline, coincidence can easily masquerade as causation. And yet, something extraordinary is happening across the volcanic world. Mount Etna has once again demonstrated why Europe's largest active volcano remains one of the most closely watched volcanic systems on Earth. During August, explosive activity and ash emissions affected the summit region, while effusive activity occurred from vents associated with the Valle del Bove. Aviation authorities raised concern because ash is not merely a visual phenomenon. Fine volcanic particles can damage aircraft engines, contaminate air filters, and create serious hazards for flight operations. Etna's activity therefore transformed a geological event into an immediate technological and economic problem. Etna is also a perfect example of why the solar volcano question cannot be treated casually. The volcano was already active before the M8.1 solar flare on August 20th. That chronology prevents a simplistic claim that the flare caused Etna's eruption, but it does not eliminate the possibility that solar variability might influence some component of volcanic behavior on different timescales. Etna possesses a complex plumbing system, and eruptions are controlled by magma supply, pressure, volatile exsolution, conduit conditions, and structural pathways. If external forcing matters, it would most likely act as a secondary influence within that much larger system. Guatemala's Fuego presents another piece of the puzzle. In early August, the volcano intensified enough to prompt preventive evacuations from communities exposed to volcanic hazards. Fuego is one of the most persistently active volcanoes in Central America, and its frequent explosions make it a natural laboratory for studying how volcanic systems transition between different states of activity. When a volcano that already erupts frequently becomes more energetic, scientists can examine changes in seismicity, gas emissions, lava behavior, explosive frequency, and ash production. The challenge is determining whether any external environmental variable consistently accompanies those changes. Then there is Taal, a volcano whose behavior deserves particular attention because of the way magma, water, fractures, and seismicity interact beneath a relatively compact volcanic complex. Reports around August 15th indicated 74 volcanic earthquakes in 24 hours. That does not mean an eruption was inevitable, nor does it mean 74 earthquakes represented 74 separate magma intrusions. Volcanic earthquakes can have different origins, and interpretation requires station data, waveform analysis, deformation measurements, gas observations, and other monitoring parameters. Still, a sharp increase in volcanic seismicity is exactly the sort of signal that volcanologists watch carefully. A volcano can remain active at low levels while undergoing periods of increased unrest. Volcanic systems breathe, expand, contract, fracture, degas, heat hydrothermal fluids, and redistribute pressure even when no lava reaches the surface. The transition from quiet unrest to eruption may involve subtle changes that unfold over days, months, or years. If an external forcing mechanism exists, researchers would therefore need to determine whether it changes measurable parameters such as earthquake rate, deformation, gas flux, or eruption probability, rather than merely producing a dramatic headline. Colombia's Puracé adds another important observation because elevated seismicity accompanied changes in volcanic gas emissions and led authorities to raise the alert level to orange. That combination is more informative than seismicity alone. Earthquake swarms can occur for many reasons, but when seismicity is accompanied by changes in gas chemistry or flux, deformation, thermal output, or other independent indicators, the evidence for genuine volcanic unrest becomes stronger. A solar volcano hypothesis would ultimately have to explain these measurable physical changes. It would need to show not merely that volcanoes become noisy during solar disturbances, but that their internal behavior changes in a reproducible way. Hawaii's Kīlauea provides an entirely different control case because it has remained actively erupting. USGS reporting around August 20th indicated continuing lava activity within the summit crater, accompanied by minor earthquakes. Kīlauea therefore cannot be described as a volcano that suddenly awakened because of the latest solar event. It was already erupting. Yet persistent volcanic activity is scientifically valuable because it provides a continuous background against which environmental fluctuations can be compared. If solar disturbances influence eruption intensity, lava output, seismicity, or degassing, a continuously active volcano could potentially reveal those changes more clearly than a volcano that spends decades in relative silence. Indonesia adds another layer of complexity because its volcanic arc contains an extraordinary concentration of active systems. Semeru, Ibu, Dukono, Krakatau, Lewatobi, and other volcanoes have remained active or restless during the same broad period. That clustering can look spectacular on a global map, especially when solar activity is displayed beside it. But Indonesia is located along some of the planet's most intense subduction zones, where oceanic plates descend into the mantle and generate enormous quantities of magma and hydrothermal activity. A high volcanic background rate is therefore expected. The challenge is detecting anything above that already elevated baseline. Earth has hundreds of potentially active volcanic systems, and dozens can be erupting or restless at any given time. Somewhere on the planet, earthquakes are occurring continuously. Somewhere, magma is moving. Somewhere, a volcano is releasing gas. Somewhere, a new lava flow is forming. Therefore, finding several volcanoes active during a solar disturbance is not surprising by itself. The scientific signal would be an abnormal increase above the expected background rate, synchronized within a physically plausible time window. The distinction between a solar flare and a coronal hole high-speed stream is equally important. A flare is primarily an intense burst of electromagnetic radiation produced by magnetic energy release in the solar atmosphere. A coronal hole, by contrast, is a region associated with open magnetic field and enhanced solar wind outflow. A coronal mass ejection is a massive expulsion of magnetized plasma. These phenomena can occur together, but they are not interchangeable. A volcanic study that combines all solar disturbances into one category risks obscuring the mechanism. The Earth may respond differently to radiation, particles, magnetic compression, and sustained solar wind forcing. The August solar environment illustrates that distinction beautifully. The Belgian Space Weather Center reported that one coronal hole was crossing the central solar meridian and that an associated high-speed stream could reach Earth beginning around August 21st. Historical solar records also show that other August coronal holes produced high-speed streams with measurable geomagnetic consequences. One documented stream reached roughly 604 kilometers per second, equivalent to about 375 miles per second, while producing minor geomagnetic storm conditions. These are not hypothetical solar wind speeds. They are measured components of the Sun-Earth environment. The Sun's magnetic field can therefore disturb Earth without an enormous flare. A coronal hole stream can arrive like a sustained river of charged particles rather than a single explosive bullet. When its magnetic field interacts favorably with Earth's field, energy can enter the magnetosphere. The interplanetary magnetic field's north-south orientation, particularly the BZ component, is critical because sustained southward orientation can couple efficiently with Earth's magnetic field. This is why two solar events of similar apparent strength can produce very different effects at Earth. Geometry, magnetic orientation, speed, density, and duration all matter. During August, these interactions were measurable. solar wind speeds rose during periods influenced by coronal hole streams and other disturbances, while geomagnetic activity reached active and minor storm levels. The Belgian data recorded a minor storm interval around August 18th, with NOAA KP reaching 5. That is not a catastrophic geomagnetic storm, but it proves that the solar wind environment was capable of disturbing Earth's magnetic field during the same general period in which volcanic unrest was being reported around the world. The question then becomes whether such disturbances can somehow reach deeper Earth systems with enough strength to matter. One possible pathway involves electromagnetic induction. When Earth's magnetic field changes rapidly, electric fields can be induced in the conducting Earth. This phenomenon is well established and can affect power grids and long conductive infrastructure. Geophysicists know that the electrical properties of rocks vary with composition, temperature, fluids, and structure. Magma and hydrothermal fluids are especially conductive compared with many surrounding rocks. That makes volcanic systems interesting from an electromagnetic perspective. If changing external magnetic fields induce currents in conductive zones beneath volcanoes, researchers can at least formulate a physical hypothesis that can be tested using observations and models. Another possible pathway involves atmospheric and ionospheric coupling. Solar energetic events can modify ionization, alter electrical currents, and disturb the upper atmosphere. Earth evolution's Schumann resonance measurements sit within this broader electromagnetic environment, although the site correctly warns that local effects and instrument noise must be separated from genuine global signals. The challenge is tracing a disturbance from the ionosphere downward through the atmosphere and crust without invoking an energy transfer that is physically implausible. A compelling mechanism must explain both the magnitude of the forcing and the efficiency with which it reaches geological depths. Tidal forcing offers another analogy. Tides can influence certain geological processes because the Earth-Moon system produces predictable periodic stresses. The key lesson is not that solar storms are equivalent to tides, but that geological systems can sometimes respond to relatively small changes when they are already close to a critical threshold. A tiny perturbation may be insignificant for one volcano and meaningful for another. That possibility is why researchers often talk about modulation rather than direct triggering. A solar disturbance might, in principle, alter the probability or timing of an event without supplying the enormous energy required to create the underlying volcanic system. The concept resembles dynamic triggering in seismology, although the mechanisms are not identical. A large earthquake can send seismic waves through distant regions and occasionally perturb faults that are already close to failure. The incoming waves do not create the tectonic stress accumulated over centuries. Instead, they may alter the timing of rupture. Solar forcing, if eventually demonstrated to influence volcanic or seismic systems, would likely require a similarly subtle interpretation. It would not mean that a solar flare possesses enough energy to manufacture an earthquake or eruption. It would mean the external disturbance could potentially alter the timing of a system already approaching instability. That distinction also explains why the search for solar-earthquake relationships has persisted despite skepticism. The Earth is a nonlinear system. Nonlinear systems can amplify small perturbations under particular conditions, but they can also suppress them completely. A disturbance that produces a measurable response in one environment may disappear into background noise in another. The challenge is not merely detecting a correlation. Scientists must determine whether the response is reproducible, whether the timing is physically reasonable, whether the effect survives statistical controls, and whether laboratory or numerical models support the proposed mechanism. Some researchers have already reported intriguing statistical relationships. The long-term volcanic study mentioned earlier found a strong correlation between volcanic eruption frequency and a component of the solar background magnetic field over many solar cycles. That does not prove that a flare triggered an individual eruption, and it does not establish the physical pathway. But it does suggest that solar variability and terrestrial volcanism can be compared quantitatively rather than dismissed simply because the two systems seem disconnected. The next step is to test whether the relationship survives independent datasets, alternative statistical methods, and physically grounded models. The same principle applies to earthquakes. A magnitude increase represents an enormous change in seismic energy, and Earth Evolution's Seismic Analytics page emphasizes that a 1-unit magnitude increase corresponds to roughly 32 times more released energy. That nonlinear scaling means a few large earthquakes can dominate a global energy calculation. Consequently, researchers looking for solar modulation must carefully distinguish event counts from seismic energy. A solar disturbance might coincide with more small earthquakes without affecting the global seismic energy budget, or it might appear correlated with large events simply because large earthquakes naturally cluster. Space-based observatories continuously watch the solar disk in extreme ultraviolet and other wavelengths. Earth Evolution's current solar analytics draw from NASA and the European Space Agency's Solar Dynamics Observatory observations, including intensity-grams and magnetograms that reveal the sun's magnetic structure. A magnetogram can show where magnetic polarities emerge, collide, twist, and reorganize. The dark coronal hole regions seen in extreme ultraviolet are therefore not empty holes. They are visible signatures of a magnetic topology that controls how plasma escapes into space. There is another reason the sun deserves attention right now: solar cycle behavior. The sun follows an approximately 11-year cycle in sunspot activity, although the magnetic cycle is roughly twice that length. During active phases, the number of sunspots, flares, coronal mass ejections, and other disturbances generally increases. Solar cycle 25 has produced several periods of intense activity, reminding scientists that the modern technological world is deeply dependent on accurate space weather forecasting. Satellites, aviation, navigation systems, electrical grids, communications, and spacecraft all operate within the sun's changing environment. Understanding that environment is no longer merely an astronomical curiosity. The same expanding observational capability is now being applied to Earth. Ground stations continuously measure magnetic fields, seismic signals, atmospheric electricity, ionospheric conditions, and other variables. Satellites observe solar radiation, magnetic fields, energetic particles, and the solar wind. The result is an unprecedented ability to compare what happens on the sun with what happens on Earth in near real time. A century ago, researchers might have noticed that an aurora appeared on a particular night. Today, they can trace the solar eruption, measure the interplanetary magnetic field, monitor magnetospheric currents, watch ionospheric disturbances, and compare those changes against geological instruments distributed across the planet. That technological revolution changes the debate. Solar volcanic research no longer has to rely exclusively on historical eruption catalogs and sunspot records. Modern scientists can examine high-resolution solar imagery, magnetograms, solar wind measurements, geomagnetic indices, satellite particle data, global seismic networks, volcano deformation measurements, gas sensors, thermal cameras, and continuous acoustic records. The datasets are enormous. Machine learning and statistical methods can search for subtle relationships that humans might overlook, but those tools also increase the risk of finding false correlations. The more variables researchers examine, the easier it becomes to discover patterns that appear significant by chance. A particularly powerful approach would be to construct a global volcanic response index and compare it against multiple solar drivers separately. Instead of simply counting eruptions, researchers could weight seismicity, deformation, gas emissions, lava output, eruption frequency, and explosive intensity. Solar variables could include sunspot number, flare class, X-ray flux, coronal hole area, solar wind speed, interplanetary magnetic field strength, BZ orientation, geomagnetic indices, and energetic particle flux. Then researchers could search for relationships across multiple time lags. If a signal appeared consistently across independent volcanic datasets, it would become much harder to dismiss. The biggest obstacle would remain physical mechanism. Statistics can reveal that two variables move together, but physics must explain why. Suppose volcanic activity increased after geomagnetic storms. Scientists would then need to identify a pathway capable of transmitting the disturbance from the magnetosphere to the volcanic system. That pathway could involve electromagnetic induction, atmospheric electric effects, fluid movement, stress modulation, or some combination. Each possibility would have to be quantified. How strong is the induced field? How deeply does it penetrate? How much energy reaches conductive magma? How large is the resulting pressure change? Is that perturbation sufficient to influence a system near failure? This is also why the August 2026 events are so valuable as a natural experiment. The Sun has produced significant activity, including coronal hole streams and the M8.1 flare. Earth's magnetic environment has responded with measurable disturbances. At the same time, multiple volcanoes have displayed significant activity. The coincidence is real. The question is whether it is statistically exceptional. If the volcanic rate during comparable solar conditions is no higher than normal, the apparent connection may be coincidence. If the rate is consistently elevated across a large historical dataset, the coincidence becomes a signal worthy of deeper study. For now, the evidence gives us something more interesting than a simple answer. The Sun has been active. Coronal holes have produced high-speed solar wind streams. Earth's magnetic environment has experienced measurable disturbances. A powerful M8.1 flare erupted from AR 4513. And across the same broad period, several major volcanic systems have displayed significant activity or unrest. The chronology does not support saying that one solar flare caused one volcano to erupt, but it does justify continuing to examine whether solar variability can modulate Earth's already unstable geological systems. The volcanoes themselves are now the witnesses. Etna is releasing ash and lava from one of Europe's most active volcanic systems. Fuego continues demonstrating the violent energy stored beneath Guatemala. Taal has produced an alarming pulse of volcanic seismicity. Puracé has entered a heightened alert state. Kīlauea continues to pour molten rock into its summit environment. Indonesia's volcanic arc remains crowded with eruptions and unrest. Each system is different, yet each is being monitored with increasingly sophisticated instruments. Their combined data may ultimately tell us whether the solar disturbances above are merely passing visitors or subtle participants in a much larger planetary system. And above them all, the Sun continues turning. Its magnetic field twists through plasma hotter than anything naturally found on Earth. Dark coronal holes rotate across its surface. Open magnetic field lines release solar wind into space. Sunspots grow, decay, and occasionally unleash enormous flares. Every eruption sends information outward at the speed of light, followed later by particles and magnetized plasma that may cross the distance to Earth. We are living inside the extended atmosphere of a star, whether we notice it or not. The question is not whether the Sun reaches Earth. It unquestionably does. The deeper question is whether some part of that influence reaches farther than scientists once assumed. If solar storms can measurably alter the probability of volcanic or seismic events, the consequences would be profound. Forecasting would become a multidisciplinary problem, connecting heliophysics with volcanology, seismology, atmospheric electricity, geomagnetism, and planetary science. Solar observations could become another variable in volcanic hazard research. Space weather forecasts might someday be examined alongside tectonic and volcanic monitoring. The prediction would still never be simple, but the data feeding the probability models would become much richer. For now, however, the responsible conclusion is neither dismissal nor certainty. The Sun has supplied a remarkable sequence of measurable disturbances, and Earth has supplied a remarkable sequence of geological responses. Several volcanoes were already active before the strongest recent flare, which means the relationship cannot be reduced to a simple cause and effect chain. Yet long-term statistical research has reported correlations between solar variability and volcanic frequency, while modern instruments now make it possible to test such relationships with far greater precision than ever before.